Welcome to the AI Checkpoints. We are diving deep today into one of the really big challenges in AI right now.
Mm,
How do we give these LLM agents, a proper memory,
yeah,
something lasting, something that evolves? Because, these large language models, they're amazing. They can reason, they can use tools, but they often just hit this fundamental wall. They're stateless. It's almost like having this really great conversation with someone, but they forget everything you told them 5 minutes ago.
exactly.
So for these complex ongoing tasks, how do we actually give them that persistent understanding, that long-term recall?
Good.
That's really what we're trying to unpack here.
It really is. And for AI agents to genuinely move beyond just, simple chats and become truly capable, reliable, believable even. Memory isn't just a nice to have. It's absolutely foundational.
Right.
Think about us, human intelligence,
Yeah.
our ability to learn from the past, adapt based on new stuff, build this cumulative understanding. For AI, we're not just talking chat history.
Mhm.
We need persistent, evolving knowledge
Mhm.
that actually informs what the agent does next.
Yeah.
It's about turning those stateless apps into something with real memory, like Richmond Lake from MongoDB really hammered home in his talk on architecting agent memory.
Okay, so to help us navigate this whole landscape, we've looked at some great sources. There's a discussion from the MLOS community, some really interesting talks from the AI Engineer YouTube channel, and a conceptual overview from LangChain, too.
Good stuff.
So yeah, let's unpack this. How can these agents not just remember, but actually learn, evolve even?
Okay, let's ground this. Think about an example, kind of like the one they discussed in the MLO piece community session on AMEM. Imagine an AI agent acting as a DevOps engineer.
Okay.
It's looking after this huge, complex infrastructure, right, over months, maybe years. Now, if a system crashes, the agent can't just fix the immediate thing.
Right, it needs more context.
Exactly. It needs to look at logs, diagnose, maybe suggest, hey, let's increase memory for the auth service. And then, this is key, it needs to learn from the result, especially if a human says, yeah, good idea, approves it, and it works.
Ah, so it remembers that success.
Precisely. So the next time something similar happens, it doesn't start from square one. It recalls that past solution, the feedback, and uses that built-up knowledge. And that really highlights the core challenge. LLMs are great at reasoning, using tools, within their current context window, but they just lack that built-in, persistent long-term memory for the outside world. Their default is, well, stateless.
Stateless, yeah.
So each interaction is basically processed on its own, with no memory of past inputs or outputs unless you specifically engineer it in. And that gap, it pops up in all the sources we looked at.
And that's where it gets frustrating for users, right? Like
Mhm.
Richmond Lake pointed out, current LLM apps just hit this wall because they don't natively remember anything beyond the immediate prompt. You end up just repeating context over and over. It's so inefficient. The goal isn't just stuffing everything into a limited context window. It's about retrieving the relevant memory right when you need it.
Exactly. Now, people have tried things. You see memory solutions using graph databases, tools like Mizero,
Yeah, I've heard of those.
and they're useful, sure. But the MLOP-DOS community paper raises a really critical point. They often depend on these rigid, predefined schemas.
Meaning you have to decide the structure up front.
Pretty much. You have to map out your knowledge base in advance. But I mean, real-world knowledge isn't like that, is it? It's messy, dynamic, new facts, new connections pop up all the time. That inflexibility makes them maybe less suited for systems where knowledge really needs to grow and change.
Okay, and this is where AMEM comes in. You mentioned that earlier.
Right, AMEM, agentic memory. It's aiming for something more universal, more flexible. And the really interesting part, it's inspired by the Zettelkasten method.
Zettelkasten.
Yeah.
That's German, right? Like notebox or something.
Exactly, slipbox. It's this old idea famously used by a German sociologist, Niklas Luhmann. Apparently, he managed something like 90,000 index cards.
90,000, wow.
Yeah. The idea is you link these small atomic notes together. You create this complex web of interconnected ideas, like building your own personal Wikipedia, one idea at a time, but with links that grow.
Huh. So the MLOps discussion, did they think that's how we remember things, or is it better for AI? I feel like my brain's way messier than 90,000 organized cards.
Huh. Yeah, maybe our human brains are a bit more
Hmm.
creatively
Wow.
chaotic, as you put it. But the AMEM process itself is pretty systematic. It starts with content ingestion. That's just the raw input, maybe a bit of conversation.
Okay.
Then comes LLM enrichment. This is super important. The LLM takes that raw stuff and makes a memory note. It adds context, generates relevant tags. Like if you talked about photography, you might add tags like hobby photography, maybe keywords like scenery.
So it's adding meaning, not just storing raw text.
Precisely. It transforms raw data into these semantically rich, linkable little knowledge atoms. That lets the agent build up a nuanced understanding, not just store isolated facts. That's the real kicker with AMEM. It enables this true knowledge evolution, way beyond just static lookup.
Okay, knowledge atoms. I like that. What's next?
Next up is embedding and retrieval. That enriched node gets turned into numbers and embedding in this big multidimensional vector space.
Like a map of ideas.
Kind of, yeah. Similar ideas end up close together, so the system can quickly find other memories that are nearby, the nearest neighbors. And then the final step, evolution. This is the really dynamic bit.
This is where it changes over time.
Exactly. The LLM looks at these related memories it just pulled up and decides, do their properties need updating? Context, tags, keywords, should we form new links between these memories? This lets the whole memory system evolve, like the MLOps discussion mentioned if a president changes.
Right. Yeah.
All the related facts about the old administration can get updated. It keeps the agent's knowledge consistent and current.
Okay, so AMEM is building this structured, evolving web. But what does that actually mean for the agent's knowledge versus its memory? Is this more like a super organized knowledge base, or is it closer to how we remember, fuzzily recalling eating ice cream as a kid? It feels like it blurs the lines a bit.
That's a really sharp question. And it leads us straight to something LangChain emphasizes in their conceptual video. There just isn't a one-size-fits-all memory solution. It has to be application-specific.
Right. What works for DevOps might be useless for a chatbot writing poetry.
Exactly. So when you break down memory types, drawing from Richmond to Lake and LangChain, you see this whole spectrum. First, there's short-term memory. That's mostly about the current conversation thread.
Keeping track of the chat right now.
Yeah. LangChain calls this checkpoints. Strategies might be just keeping the last, say, 10 messages, or maybe summarizing the conversation so far with an LLM. It's about maintaining flow.
Got it. And then long-term.
Then long-term memory. That's the stuff that needs to stick around across different chats, different interactions. LangChain calls this the store. And within that long-term bucket, we're seeing these really specialized memory models pop up.
But what?
Well, things like persona memory. That's about giving agents personality, helping them build actual relationships with users. It's not just being friendly. It's about enabling trust over time, which could really change how we interact with AI.
Interesting.
Then toolbox memory. Instead of hard coding tools, the agent stores JSON schemas of available tools in a database and pulls out the right one when needed. That's how they scale up to use lots of different tools.
Makes sense.
There's also workflow memory. This one's huge for learning. The agent remembers when a task failed, which step went wrong, so it doesn't make the same mistake twice on some complex multi-step process.
Learning from mistakes, nice.
And profile or instruction memory. This lets the system update its own internal instructions based on your feedback. Like if you always edit out emojis, the system can learn, okay, don't use emojis with this user, and actually update its system prompt. Makes it much more adaptable.
That sounds like a really dynamic balancing act. And LangChain mentioned something about hot path versus background updates for long-term memory. How does that work?
Yeah, that's about when the memory gets updated. Hot path means updates happen right there in the main application logic. It's real time, but it could slow things down, add latency.
Okay.
Background updates happen separately, maybe in a different process.
Yeah.
That keeps the main app snappy, but the memory updates might not be instant.
So it's a trade-off. Real-time knowledge versus performance. You have to choose what matters most for that specific agent's job, don't you?
Absolutely. You really do. And across all these types, Richmond Lake laid out the core components: generation, storage, retrieval, integration, updating, and crucially, forgetting.
Forgetting? You mean deleting stuff?
Not exactly deleting. He made a point that maybe true deletion, like wiping a traumatic memory, isn't ideal for AI. A well-designed forgetting mechanism might be better letting less relevant stuff fade into the background without losing it entirely. It avoids overload but keeps potentially useful context accessible.
Forgetting as a feature, not a bug. Okay, that nuanced view leads us nicely to something pretty profound from Mark Bain at AI US. In his memory masterclass, he suggested the universe itself is like a network database, a graph structure, and that causal links relationships are key.
Yeah, that was a fascinating perspective.
It makes you wonder, what are we missing if we only look at semantic similarity, just finding things that sound alike? What about the deeper causal connections?
That's a critical point Mark Bain was making. He argues that while LLMs are good at finding correlations, That fuzziness from weights and biases to really understand why things happen to fight hallucinations, we need to capture those causal relationships.
And that's where graph databases come back in.
Exactly. They excel at representing relationships. It's not just about knowing two things are similar. It's about knowing how A causes B or how X relates to Y. That's vital for better reasoning, better hypotheses. It connects to what Daniel Chelliff from Graffiti calls domain-aware memory, making sure relevance is tied to specific business goals, not just fuzzy similarity.
Right, avoiding irrelevant tangents. And we're actually seeing this graph approach used in practice based on the AI engineer talks, like, Cogni.
Yes, presented by Vasilija Merovitz. They use a semantic graph built from GitHub data. They analyze developer profiles for hiring, and the agents continuously update and enrich this graph. It shows how this dynamic, evolving graph knowledge works for complex tasks.
Cool. And there was another one, Neo4j.
Neo4j MCP, yeah, Alex Gilmore showed that. They build a knowledge graph straight from conversations, capturing entities, observations, and crucially, the relationships between them. You can actually visualize the graph, which is super helpful for understanding really complex situations.
Visualizing the connections, I can see how that would help.
Definitely.
And Daniel Chelliff from Graffiti and Zep AI, he really hammered home that point about domain-aware memory, didn't he? That semantic similarity isn't always business relevance.
He really did. His example was great in Agent remembering your dog's name when you're talking finance. It's technically similar maybe, but totally irrelevant. It just pollutes the memory.
Right, distracting.
So Zep's approach models explicit business objects defined by the developer using these temporal graph frameworks. It keeps the memory focused on what actually matters for the application, making retrieval way more efficient and accurate.
And that idea of temporal memory, knowing when things happen, the sequence that came up in Mark Bain's talk too, for security.
Yeah, the agentic firewall. Using episodic and temporal memory, remembering the history of commands, user behavior in a shell. The agent can spot anomalies because it knows the normal sequence of events. That makes for much smarter, proactive security.
That makes a lot of sense. Okay, so we have all these different approaches. How do we even know if they're working well? How do you evaluate this stuff?
Evaluation. That's tough. The MLO PSOC community discussion touched on this. Researchers use metrics you might know like F1 score, BLEU, RUGI.
You're like grading an essay?
Sort of, yeah. They measure accuracy, completeness of the info retrieved or generated. But crucially, they also look at cost, compute cost, financial cost of running these systems in production. AMEM, for example, apparently did well on multi-hop tasks.
Where it needs info from several past interactions.
Exactly. And it was reportedly more cost-effective than some other methods, which is obviously important.
But it sounds like there are still big question marks, right? The MLOps Q&A mentions some suspicions and challenges.
Well, absolutely. Plenty of challenges remain. Like, why do smaller models sometimes perform surprisingly well on certain memory tasks? That's a bit puzzling. There's the risk of runaway evolutions, where memory updates trigger other updates, and it just cascades out of control. How do you even define a bad memory or irrelevant info when it's constantly changing?
Yeah, good question.
Plus the practical stuff. Latency, cost at scale, integrating with existing knowledge bases, security, privacy, making sure only the right people or agents can access sensitive memories. There's still a lot to figure out.
It really sounds like it.
You're spot on. As Daniel from ZPI said, there's no one-size-fits-all memory solution. And evaluating these agentic systems is just inherently hard because they aren't always predictable. It takes a lot of careful, nuanced testing.
Okay, so before we wrap up, Mark Bain's talk had that really wild physics-based idea. The equation. Memory times compute equals I squared.
Ah, yes, the imaginary unit connection.
What was the idea there? Something about asymmetry.
Basically, his thought was that perfect symmetry, perfect predictability would mean, well, nothing could really happen. Maybe we wouldn't even exist. It's the asymmetries, the fuzziness, the approximations in the universe that create causality, that allow things to happen.
And that connects to LLMs.
And it allows for the mechanisms that make LLMs work, their ability to handle fuzziness.
Yeah.
And maybe, just maybe, it's fundamental to how our universe works too. It's definitely a mind-bending thought to leave folks with.
Wow, yeah. Definitely something to chew on. What a journey we've taken today. From just understanding why AI agents need memory so badly, to exploring these complex solutions like AMEM, seeing the power of graph databases for those crucial causal links, and looking at all the different ways memory can be architected. It's really clear that building smart, truly capable AI hinges on cracking this memory code.
Absolutely. And while there are definitely big challenges still, evaluation, managing complexity, cost, the progress being made in helping agents actually remember, learn, and build on their experiences. It's incredibly exciting. It points towards a future where AI isn't just reacting moment to moment, but really understanding context and building more meaningful interactions.
So definitely keep an eye on this space. Memory management is fast becoming a central pillar of AI engineering, and it feels like we're only just scratching the surface of what's possible. Thank you so much for joining us on this deep dive into the truly fascinating world of AI memory.
My pleasure.
See you next time.